lecture, we went over a special case called Carnot cycle. We also defined what is a heat engine and what is the efficiency of a heat engine. And in our last lecture, at the end of the lecture, we went over the Carnot cycle. So just keep in mind, a Carnot cycle is by definition consists of two reversible isothermal process where the temperature remains the same from 1 to 2 and 3 to 4. And also two reversible adiabatic process. So when we say this adiabatic, we're saying from 2 to 3, we do not have any heat transfer. And from 4 to 1, we do not have any heat transfer. And for the Carnot cycle, everything is reversible. Now with that in hand, we end up by deriving the following relationship. That if we're looking at the cyclic process, 1, 2, 3, 4, we end up to have the integral of dq over t always equal to 0. So that's a quick review on what we went over last lecture. So today we want to expand our understanding on the Carnot cycle into more general scenario. It's like instead of having Carnot cycle, which is a very specific transformation, let's imagine some random cycle that is not a Carnot cycle. And our first goal here is to link any arbitrary reversible cycle. So what we know about this cycle is that it is, when we say the cycle, I'm talking about the blue curve. So that blue curve on that PV diagram shows you, okay, it is a cyclic process. Now what we want to do is link this arbitrary reversible cycle with the Carnot cycle. So this is going to be a little bit abstract. This one is more for your understanding. Now imagine on this Carnot cycle, I think I'm using the wrong note. So imagine on this reversible cycle, what we have is you pick 4 points on this reversible cycle, on that blue line, blue solid line. These gray lines are called adiabats. So when we say something is adiabats, it means every point on that gray dotted line will be adiabatic transformation. So that means from B to D will be an adiabatic process. From N to S will be an adiabatic process, or MACR will be adiabatic process. So everything along that gray curve will have Q equals to 0. At the same time, we can also find out pairs of isotherm. All right, so the first thing, gray one is the adiabat curve, adiabats we defined. The blue one is the reversible cycle, and the green one are called isotherm. What it means is for this green line, what they have is they have the same temperature. Or in this diagram, you can also imagine they have the same area under what we have here, like AM and B, AM and B. So that's a path we're taking, and we're manually set like that equals to the area under AB when it's infinitesimal small. All right, so right now what we have is MN are isotherm with each other. They have the same temperature. RS are isotherm with each other. They have the same temperature. And let's go one by one. You might want to take a picture of this cycle, so when I write on something below, you have an idea about what the cycle looks like. Or maybe I can just write it on the board. It might be easier. So one of the things we have is we have the area under the curve. And for a reversible cycle, the area under the curve gives you the work reversible. So in this case, we know the area under the curve for AM and B and AB are the same. For RCDS and CD are the same. So what we have is work reversible. So WAB equals to WAM and B. And likewise for the other pair as well, if you can. WCD equals to WRCDS. All right, that's just one information. The second information, so this one is talking about work. Second information is about our internal energy. So now internal energy U is a state function. When we say a state function, it only matters on where your start point is and what your end point is. So naturally, if you look at these relationships from AB to AM and B, you would have delta U AB equals to delta U AM and B. It's path dependent. It is a state function. We don't care how it gets from A to B. All right. And thirdly, we can apply our first law of thermodynamics, where you have delta U equals to Q plus W. So now what we know is delta U AB equals to delta U AM and B. Work AB equals to work AM and B. So using the first law of thermodynamics, we get information about heat. So here we have QAB equals to QAM and B. All right. Then what we know on the adiabats. So again, what we have, whenever you have something along the adiabats, what we know is they have Q equals to 0. So if we look at the points along the adiabats, what we have QAB, well, QAM. So these point A and point M are along the adiabats on that curve that equals to 0. And also QBN equals to 0. For like CR and SD as well, those are the other two pairs, yes?
It's really hard to see what you're writing on the chalkboard.
Yeah, I'm sorry, but maybe you can just come a little bit forward. You can also find all these in the annotated notes.
I think there's a light switch to turn
Oh, sorry, I thought you were talking about I'm writing too small, but let's see. Okay, is this one better?
Yeah.
Okay. All right. Where were we? Yes.
Is QCA also 0?
QCA, yeah, QCA will also be 0. But right now, let's just focusing on the top part. Whatever we derive for A, B, and N will also similarly apply to CDRS. Okay, I'll pause a little bit before we move on. So first of all, we manually set this isotherm. So we have the area below the curve are the same. And because those areas are the same, on the PV diagram, for a reversible process, that area is the reversible work, right? So we have the work being the same for the process AB and AM and B. That's the first piece of information. Second piece, the internal energy is a state function. So it doesn't matter how you get from A to B. So these are just always the same for your internal energy, which is a state function. And then using the first law of thermodynamics, you got delta U equals to Q plus W, and you get an expression for QAB equals to QAM and B. And then, because we predefined my M and A are on the same adiabats, B and N are on the same adiabats. So we have QAM equals to 0, QBN equals to 0. And then put it on here. What we end up having is QAB will equal to QMN. Right, so QAM equals to 0. So this process equals to 0. That's how you get Q and B. That gives you the QAB here. And likewise, you can apply the same logic to the bottom part of the curve to get QCD equals to QRS. And what that means is we end up having the cycle M, R, S, N is the same as the cycle to our ABCD. So ABCD is our randomly picked points on our any reversible cycle. And MRSN, if you think about it, now MR, NS, these two are adiabatic process. MNRS, these are isothermal processes. Yeah.
I was curious why like QAB and QMB don't have opposite signs. Is it the magnitudes that are equal or?
So what we're doing here is not moving the things around. What we're doing here is just saying like AN, A to M, is a zero heat process. And then N to B is a zero heat process. All right. So when we're looking at it, what we're talking about from A to B is effectively the difference between AM to N. All right, so because AM is 0, NB is 0. So if you write this out, QAM and B, you can write it as QAM plus QMN plus QNB. And this gives you the QAM and QBN. So these two terms become 0. Right, so that's why our QAB equals to QMN. All right? So everything on the board, what we're trying to show is that for any arbitrary reversible cycle, it doesn't need to be a Carnot cycle. You can somehow link that arbitrary reversible cycle with the Carnot cycle that constitute of two isotherms and two adiabatic processes. So now we have an idea about, all right, we have what these Q relationships are for our ABCD or the MNRS process. And what about the temperature? For the temperature part, we have to use our calculus a little bit. So if you look at this part, right now our RS isotherm don't have the same temperature with CD. But if you're moving these adiabats to infinitesimal close to each other, we can approximate the temperature of CD equals the temperature of RS. So that's just using calculus of moving these adiabats infinitesimal close to each other. By doing that, we end up having our final relationship that we are looking for. So that is the dQAB over TAB equals to dQCD over TCD. So when we're talking about that, we're just changing it back to the Carnot cycle. And these are the relationships we derived using the Carnot cycle. All right. So what is the conclusion here? What we end up having is now we have this random arbitrary reversible cycle, and we can find a way to equivalent this arbitrary reversible cycle to a Carnot cycle. And recall for the Carnot cycle, we have the relationship of the cyclic process dq over t equals to 0 for Carnot cycle. And now by doing what we just did on the board, we end up getting an equivalence between any arbitrary cycle to a Carnot cycle. So thus we can replace this term with any reversible cycle. All right, so the take-home message here for any reversible cycle if you take the integral of that change of Q over T, you always end up to be 0. Or, at this point, we can finally define our new state function entropy. So that is the change of heat, dq, reversible, over T. So that is our new state function, or the differential of a new state function. And again, when we're saying it's a state function, please refresh your memory on what are the state functions we talked about, like internal energy, enthalpy, or the product of PV, temperature, and so on. So the other way to put it is ds, which stands for entropy, equals to dq reversible over T. All right, and when we write something like change of entropy, what we're talking about is the change of entropy from state 2 to state 1 as S2 minus S1. What we're doing is taking the integral from 1 to 2 of this dq ReV over T. All right. And since your heat is a extensive property, so naturally your state function entropy is an extensive state function. So it matters about what's the number of mole you have in your system. All right. Any questions? Yes.
Sorry, just to make sure I got the concept right. So for reversible cycles, the change in entropy would be 0 all the time, or would it?
Well, when we're talking about 0, we're talking about, no, this one is our new state function, S, right? So for a reversible cyclic process, this term always integral to be 0. And again, it integral to be 0, well, it's a state function, and that's how we define it to be a state function. Okay, any questions? And can you all see the slides okay? If yes, I'll just leave the lights on. All right, sounds good. Now we have defined our new state function. Naturally, what we want to do, well, is how to find out what is your entropy change in different scenario. So we'll do lots of examples together and just see how do we use the definition of entropy and also whatever we learned before to find out how entropy change for different thermodynamic processes. So for this part, which is your 3.4, we are following the typical 3-step process for every example we're going to show. The first example is, first of all, well, before we jump in, is again, the idea of entropy, it is a state function. We can only calculate it using the Q reversible over T. I should have write it down here somewhere. So that means, for example, from any state 1 to state 2, what matters for the entropy change is what is the actual macroscopic property of your state 1 and state 2. They might appear to be linked by some irreversible path, but as long as we can define a reversible path from 1 to 2, we will be able to calculate entropy along that reversible path, and those delta S will be the same. All right, so that's one of the strategy we want to use. So that tells us, first of all, in order to find what your delta S is, you want to identify what is your initial and final state for your system. And then somehow you have to connect your system on your state 1, state 2 with a reversible path. And then you can use this equation to calculate what is the entropy change along the process. All right? So we will be using these 3 steps for all the examples shown below. Let's see how far we go for today. I think we have 10 different scenarios we'll be looking at together. So we'll see how far we go. First step, a cyclic process. So this one is easy. Someone want to give a guess what delta S is for a cyclic process? Right. So keep in mind your entropy is a state function. So your delta S always equals to 0. Next up, we have a reversible adiabatic process, or the 2 adiabatic process in your Carnot cycle. This one is also pretty straightforward. So your dq reversible equals to 0 because it's adiabatic process. So naturally, your ds equals to 0 and your delta S also equals to 0. Yes?
Our ds, if we say that that is the change in entropy, is that just this, is that always synonymous to?
Well, ds equals to dq reversible over t. So that's by definition true. And delta S is the integral of your dq REV over t. All right, but in this case, our QREV is 0, so your ds is 0, and your delta S, which is the integral of 0, also gives you 0. All right, so far so good. Let's move on. Next one, we have reversible phase change at constant temperature and pressure. So that means, for example, you have melting of ice at 0 degrees Celsius and atmosphere, or you have vaporization of water at 100 degrees Celsius and regular atmosphere. So how do we calculate it? So in this case, we want to first write down, we know that Q REV, so at that constant temperature and pressure, or at that melting point or boiling point, you have QREV just equals to your delta H equals to QP, or I should say QP equals to delta H, right? It's constant pressure, so your heat reversible just equals to Q, or heat transfer at constant pressure, which in this case equals to delta H. And you can use our equation, delta S equals to 1, 2, dq REV T. It's also at constant T, so we can take that temperature out from the integral to be 1 over T, 1, 2, dq REV, or it just gives you 1 over T QREV. And in this case, that just gives you 1 over T delta H. And let's try apply what we just derived here. So one of the things is, if you're going to remember anything for this process, like maybe you can just remember this one. For the reversible phase change at constant temperature, you don't have to remember that last relationship, but it's okay. I mean, it's on your own formula sheet. Whatever works for you works for me. I don't care what you put on your formula sheet, but make sure you have it in a format that you can follow. Let's do the example here. We're saying the heat of vaporization of water at 100 degrees Celsius is 40.66 kilojoule per mole. Now the question asks you to find the delta S, or the change of entropy, when 5 grams of water vapor dense to liquid at 100 degree and 1 atm. So it gives you the heat of vaporization. It asks you to find the delta S of condensation. So one of the things we can use is delta H condensation equals to negative delta H vaporization equals to negative 40.66 kilojoule per mole. Right, and then you have two ways to do it. First of all, you can try your actual delta H for this 5 gram of water. You convert it first, or you do the delta S calculation first. So delta S condensation that we just worked out equals to, well, delta H over T. But in this case, this is the delta H we'll be using. And that just gives you negative 40.66 kilojoule per mole, and divided by temperature, which is 100 plus 273. That gives you negative 109 joule per mole per Kelvin. So that's for 1 mole of water condensation. That's the entropy change. And naturally, you can do the calculation for 5 gram of water. Just like convert that 1 mole into 5 gram of water. And I trust you can do that, so I don't have to go with you. All right. Then let's move on to some new examples. We can also have reversible isothermal processes, which are the 2 isothermal regions on our Carnot cycle. So this one, again, we're using the definition here. We're always using this definition of delta S equals to 1 to 2 for a reversible process, dqReV over T. Now, if we know it is a ideal gas, we might be able to express it. But if it's not an ideal gas, what we can do is just take that temperature out from the integral because it's a constant isothermal process. And that becomes, well, T over 1. And you integral dqReV and ends up to be qReV over T. All right. Next up, isobaric heating. So isobaric heating, just say, well, you have a cup of water or a cup of coffee, if you like, and just heat it up at normal atmosphere. Yes?
How is the graph for the reversible isothermal process different than the reversible adiabatic one?
What do you mean here?
Yeah.
Well, isothermal means your point A and 2 have the same temperature. Adiabatic means between your 1 to 4 or 2 to 3, they have no heat.
Got it, okay.
They're just like different in nature.
Okay.
You can easily imagine something that is isothermal when their temperature are the same. Or you can easily imagine a system is adiabatic if it is like covered by adiabatic wall, or there's no heat transfer between the system and surrounding. So these two are just 2 different thermodynamic processes.
Okay, thank you.
And that's our Carnot cycle, by the way. So you can go back to lecture 6 and review it a little bit. Okay. Next one. This one is where we start to use our hypothetical reversible path assumption. So what we have here is, it didn't tell you it is a reversible process. But in your textbook, it did a very good job of how to link something that looks irreversible to a reversible process. Your textbook did a very good job in how to build that hypothetical reversible path. So what we have to do here when we're working on the derivation is we can assume some kind of hypothetical reversible path exists. All right, that's like the Joule-Thomson experiment. The total process is not reversible, but you can set up a process so every step of the way it is reversible. So likewise here, if you're isobaric heating for a cup of water, if you heat it very, very slowly, then you can imagine that's being a reversible path. So what we know, it's isobaric, so at constant P, what we have is dq reversible now equals to dqp. And at constant P, naturally we can use Cp dt. So our delta S gives you 1 to 2 dq reversible over T, 1 to 2 Cp dt, Cp over T dt. And applying this relationship, you can get, let's do an example question together. The question itself is pretty short. It's find delta S when 100 grams of water is reversibly heated from 50 degrees to 75 degrees Celsius at 1 atm. And it's given that the Cp, or the isobaric heat capacity of water, is constant at 1.00 calorie per gram per Kelvin in temperature range from 25 degrees to 75 degrees at 1 atm. So what that tells me is, okay, so Cp is constant for what we care about, right? It's 50 to 75, that's within the 25 to 75 range, so we can assume Cp is a constant. So our delta S, which we derived above from 1 to 2, Cp over T dt becomes Cp 1 to 2 1 over T dt. And doing that integral, you get Cp ln T2 over T1. And again, I mean, just if you think about this process, we could easily replace what we tell you about like CPT being a constant to something like, okay, CPT now is a function of temperature, and do the integral likewise, right? It's just the same logic. Next up, then let's look at the more general thing about the reversible change of state of a perfect gas. So when we say change of state, we're talking about change of the thermodynamic state. That means when we say a thermodynamic state, we're talking about my perfect gas have a different combination of pressure, volume, and temperature. We want a general expression of delta S. So by definition, we have ds equals to dq ReV over T. Or using our first law of thermodynamic, dq ReV equals to du minus dw reversible. Now for a perfect gas, there are lots of things we know. For reversible process, we have d reversible, dw reversible equals to negative pdv. And your du for a perfect gas equals to cv dt. Now I want to quickly clarify one thing here, is that although we measure our heat capacity at constant volume or constant pressure for Cv and Cp, when we're using this heat capacity, we do not have to limit ourselves to say, I can only use CV at constant volume. So that's not something you have to limit yourself, right? So once you measured CV at a constant volume, you can always use it as some other scenario. Okay, next up, let's write that out. We have CV dt plus PdV, and here our P for ideal gases equals nRT over V. Right, so we can further write it out as CV dt plus nRT over V dV. And for ideal gas, your CV is constant. So, taking together, what we have, the expression of ds, that gives you CV over T dt plus nR over V dV. So that's just moving this 1 over T or Q reversible over T here. And naturally, you could imagine the next step is to take the integral on both ends of this equation. So on the left, we have integral ds CVT over T dt plus nR over V dV. So on the left, integral of ds gives you delta S. Here CV is a constant, so we take it out. Integral of 1 over T dt gives you ln. We can take it out for perfect gases. What we have is and on the right-hand side, we have nR 1 over V dV. You take the integral. You have the ln V2 over V1 for perfect gas. Yes.
For the second line to the third line, could you please explain how the T moved to the lower CV?
We didn't move anything.
Oh, sorry.
It's just dq reversible equals to CV dt plus nRT over V dV. Now your ds equals to dq over t. So you have to divide by t for both terms. Okay, how are we feeling so far? Like halfway through? Okay. Next up, we have our reversible change of state of irreversible change of state of a perfect gas. So we just went over our process of saying, okay, what's the general relationship for change of state for a perfect gas that's reversibly? Now, if you're talking about irreversible processes, it's actually the same matter. You just have to somehow dream a reversible path in your mind. So to connect your state 1 and 2 for your perfect gas. As long as it is something possible, you can always assume it is reversible process and just taking that reversible path for it to take place. So what that means is if we end up having these kind of problems, like now we have the Joule experiment, which is actually an irreversible process, right? That's an expansion of your perfect gas into vacuum. But as long as you can imagine it takes place along a reversible process, you can use whatever we derived for the reversible process to calculate the entropy change. Let's actually see an example here, because I know it feels like really abstract. I'm going to skip this one, but I'll just use our 0.9 as an example. Number 8 in your textbook will be skipped until we reach like 4.5. So this is the example we are talking about. So it asks you to find delta S for the conversion of 10 grams of supercooled water at negative 10 degrees Celsius and 1 atm into ice at negative 10 degrees Celsius and 1 atm. It gives you the average CP value for ice and supercooled water. And now the question is, how do you find out the entropy for this process? We do not have a direct way to do it because the process appears to be an irreversible process. But how do we construct a reversible path on paper? Now, this is how we do it. Our initial state is supercooled liquid water at negative 10 degrees Celsius, P equals to 1 atm. Now, pressure stays the same for the whole time, so I might just drop the pressure. And your final state, you have solid water at negative 10 degrees Celsius at 1 atm. And this transformation is irreversible. That's one piece of information that we cannot directly plug in. And the second piece is we do not have the CP value for that, yes.
Oh, why does it say TF equals 1?
That's final.
Should it be PF? That's below.
Oh, yeah, okay. All right, so because it is an irreversible process, we can't just directly use our Q reversible. And what we want to do is how to build a process. So now let's imagine the first step here. So you can imagine it to be an isobaric, reversible heat of water to 0 degrees Celsius. So what we're doing here is just, now you have supercooled water at negative 10. We'll reversibly heat up that water to 0 degrees Celsius, which is something that can be easily done if you control the temperature or the heat source like slow enough. So in our state 2, our temporary state 2, we will have T2 equals to 0 degree or 273 Kelvin. My water is liquid. My P2 is 1.00 atm. All right, so that's the first step. Now we need a different reversible process. Now we have raised the temperature of our supercooled water to 0 degrees Celsius, which is a melting point of water, well, ice, melting point of ice. So you can now imagine a reversible phase change between water and ice at 0 degree, which is the melting point. All right. And after that reversible phase change, we have T3, which is also a temporary hypothetical state, equals to 0 degrees Celsius or 273 Kelvin. It's now solid with P3 equals to 1.00 atm. Someone want to guess what the next step is? We need one more reversible step to link your temporary state 2 with your final state. Now your water is already ice, yes? Well, it's already in solid. We want it to be solid in its final state. We'll just decrease the temperature of your 0 degree ice to negative 10 degree in a reversible path. So that's our C. It's again a isobaric, reversible cool of ice to negative 10 degrees Celsius. Now, for all these three steps, we have enough information for us to solve for the entropy change between 1 to initial state to 2, 2 to 3, 3 to final state. Right, so that's what we mean but when we're saying for an irreversible process, as long as you can build a reversible path to that final state, you will be able to solve for the entropy change. Yeah.
Why is this an irreversible?
Now, if you think about your supercooled water at negative 10 degrees Celsius, it can once it goes to ice, because the temperature is lower than your melting point, it can't go back to its original state. Likewise, right, if you have 200 degrees Celsius of water liquid, which is super hot, the transformation of that super hot liquid into vapor is also irreversible. Now I'm going to quickly go over how to solve it, how to set up the calculation for this problem. You can try it yourself and compare your answer, well, either with the textbook or with the annotated notes. Now, for our process A, again, we have the isobaric reversible heat of water. So my delta S1 equals to 1 to 2 dq ReV over T. And in this case, what is our QReV? At constant pressure, your QReV just equals to QP. And again, for this process, for at constant pressure, you have an idea about how to calculate that QP for our first step. Next up, we have delta S. Now this one is a phase change, and we covered it earlier today at number 3, I think. Yeah, so at number 3, we derived it to be delta H over T. So when we know what the heat of vapor melting, or do I have melting? Yeah, I'll give you the heat of fusion in this problem, and you get an idea about what that heat of fusion or melting is for this process. And you can calculate the delta H at the same temperature. Well, plug in delta H and T, you get the delta S for the second process. And C is effectively the same as A. You're just plugging different numbers for that process. All right, so this is a demonstration in like, when we're looking at something that feels, you don't know how to approach because it's irreversible, just try to build up a reversible path for it to take place. Okay, any questions before we move on? Yeah.
A little bit below, you wrote 3 with the circle. What does that mean?
3 is these kind of 3. So that's the equation we derived in earlier today. So that's here. This one.
Oh, okay.
Yeah. I'm just trying to link what we derived before to that new problem we're working on. Okay. And this is where I'm going to cut off for your midterm 1. We have one more example, which is the mixing of different gases. We'll save it for your later, so we'll cut off here. And we finished make up your midterm exam. So again, just tell everybody we have 5 multiple choice, 5 true and false that you don't have to provide any work. And then you have 4 short answer problems. So when we say a short answer problems, its length would be similar to, for example, this kind of question. So we give you something, and just do a quick calculation to get that answer directly. So 4 of them. and then 2 comprehensive problem, which might include multiple steps. So an example of a comprehensive problem will be something like this. It has multiple steps. We'll guide you along the way, but it contains multiple steps. You have to do several calculations for each step. There might be derivation or proof problem on your midterm exam as well. We did some of it in your discussion worksheet and also in class together. On Friday, we will have a review session, or a buffer session. Basically, we will go over what we discussed before and on topics that, and on topics I feel like people are confused. So before Friday, we have a discussion board open on Brewing Learn. So if you have some topic you are very confused about, please leave a note on that discussion board so I know what to cover on our Friday's buffer lecture. All right, so go to Brewing Learn on that discussion board for chapter 1 or chapter 2, right? Put things that you feel you're confused about. So I have an idea. I'll prepare your Friday lecture probably tomorrow afternoon. So if you want to put something on that discussion board, please do so before tomorrow noon, so I have enough time to prepare that lecture note for Friday. Yes?
Is the proof question, is that considered a short one with like a 5?
Which one?
Is a proof question like a comprehensive question?
This
Or,
one?
Like if you ask us to do